Math and Beats, another video, and this time we're going to continue with the logic discussion and discuss inductive reasoning and also counterexamples. Let's get started. First of all, let's discuss what inductive reasoning is. Inductive reasoning, well, this is a type of thought process in which we make a conclusion about future events based on patterns of past events. So it's kind of like making some type of prediction based on what we've experienced thus far. A good prediction, though. And here's an example. For example, say we were some caveman living out there and we never had no science. And every morning, the sun comes up. Every morning, the sun has risen. Then we can inductively reason that the sun will rise tomorrow morning based on what we've experienced thus far. You say, well, the sun has risen the past 500 days in a row. It's probably a good assumption to say it's going to rise tomorrow. That's some caveman math right there, but it works. Here's a specific example with some math. Consider this function here. Simple linear function f of x is 2x plus 1. But now we're going to say the domain of this function is only positive integers. Those being, if you forget, 1, 2, 3, 4, and so on. So in this list we see here, it's just a bunch of different values of the function f of x being evaluated at various values of x in its domain. 1, 2, 3, 4, and so on, all the way. We put the input of 12 in, the input of 18 in, and what we see is a pattern, hopefully you see it, is that the outputs follow this pattern, 3, 5, 7, 9, etc., seem to all be positive odd integers. And so it would seem that if we kept doing this, kind of like getting some experience about some values of the function, then inductively we could reason and make a conclusion that it seems reasonable that for every value of the function that we get, regardless of the inputs, it will be a positive odd integer. In this case, it's true. It ends up being true, and 2x plus 1's basically the definition of a positive odd integer was true. We inductively reason. You see, we see that this pattern is happening for all these different values. We haven't seen anything different. Might as well conclude that. Now, in that same example, we could even formulate a statement and say p of x is a sentence, 2x plus 1 is a positive odd integer, and then test the truth value of this statement by various values of x. So that is, we could write some type of question whether or not for all values of x, this statement p of x is a true statement. Is that true? Now, we haven't proven anything yet, but we've made a decent inductive conclusion based on what we've seen in those various values. And like I said, it ends up this is true, but we're going to have to develop a little bit more techniques to be able to actually prove it. I want to show you another example here. So a lot of stuff going on this page, but let's just take it piece by piece from the top. We got this function here, this cubic function, and we are assuming again that x is some positive integer. And then We're just going to evaluate this function at all these different values of x. 1, 2, 3, 20, 50, 100, whatever. Just keep going. Now, based on these values and some others in between and a little bit further on, I have plotted for you this graph that you see with all these dots, and those are just each dot representing specific ordered pairs satisfying x comma f of x. So for instance, you look at like f of 50 here is about 11 million and some change. That's probably about that dot right here, right there, about 50 or so, right above 10 mil. So, we got all these different points on this function, discretely defined. And it sure seems like this thing, if we keep picking bigger values of x, it is going to get bigger. And so that's what this statement is right here that I was just hiding from you, was that based on these values of x's that we pick so far, inductively, it seems reasonable to conclude that this function is always getting bigger for all values of x in this domain. That would seem reasonable because we evaluate it at many, many places and seem to be just getting bigger and bigger. We could even make a statement, sentence here, again call it p of x to represent the truth value. This function that we're looking at, f, is increasing for all values of x in its domain. And then we could inductively reason for all those values of x. P of x is true, it's always increasing. Ends up that this is false. It's a false statement. So here's an example where our inductive reasoning kind of failed us. And this is what we're really getting into, is when we inductively reason, is there a way to show that our inductive reasoning and the statement that is formulated is actually true or false? When it's false, we can show it's false by using what's called a counterexample. What does that mean? Well, it's using the assumption of what we presumably be true statement, like some inductive reasoning statement, say we presume is true, and then assuming that's true, we come up with what is called counterexample to show the statement is false. And that is some situation which shows that the statement we made is not always true. If you can find one situation where it's not true, then what that shows is that the statement we made is not always true. That last one we were looking at with the function, that cubic with all the dots and all that, it might not be obvious. If you know the behavior of cubic functions, you might have some suspicion, but just consider these values of the function right here. If I look at the value of x is 500, I get 42,016,666.67. I go up to 502 for an input. Right there, you see that those values, it shows that f of 502 is smaller than f of 500. Hence, this function starts decreasing somewhere. For how long or whatever, we don't really care. All we care about is that there is one particular situation here in which we have shown this function does not always increase, which was our presumed statement to be true. Hence, by counterexample, we have shown it to not be true because it doesn't always happen. And that's what all this stuff says right here. Function is not always increasing, and therefore we could write a statement like so. There exists some x such that p of x is not true. And hence, as an example of what is a counterexample of the original statement, for all x, p of x is true. We showed at least one of these x's makes it not true. And therefore, this statement that we made for all x, p of x, is actually a false statement because it's not always true. And then just to top this video off, we're going to look at a couple of examples of just counterexamples. We have two statements given to us here, statements A and B. In statement A, we have all mammals are land animals. What do we want to do? Come up with a counterexample of that. Well, we could think of some type of mammal that's not a land animal, like, for instance, a dolphin. A dolphin is a mammal, but it is not a land animal, at least that we know of yet. So that shows that all mammals are not all just land animals. Now, part B right here, we are given a statement, more of a mathematical statement, that the graph of every polynomial function is nonlinear. But of course, if we remember, function of the form f of x is mx plus b, where m and b are real numbers. Well, guess what? That is actually a polynomial and is linear. So we gave a counterexample of that statement. And there you have it. That is a video on an introduction to inductive reasoning and also using counterexamples to prove some statements, some specific type of statements are false. And we're going to continue on the next video with more methods of proof. Really is what we're getting into here. Once we develop all those methods, we'll start being able to actually prove some statements. So anyway, I hope it was beneficial. And now you get to listen to a short little beat. So I'm out. Later and peace.